Welcome to Colonize the Ocean podcast, where we discuss oceanic colonization, exploration, and education with your hosts Adam Jewell and Brendan Traxler.
Welcome to the Deep Dive. We take your sources articles, cutting-edge research, expert notes, and we boil them down to get you the core insights, the stuff you really need to know. Our mission, as always, is to get you properly informed, fast, maybe with a few surprising facts along the way. Today, we're diving deep, really deep, into something that's fascinated people forever. This idea of living under the sea. If you've ever pictured yourself looking out from a base, like in the abyss, or maybe you remember that scene in Star Trek IV, Captain Kirk needing transparent aluminum for the whales.
Oh, yeah, classic. Scotty's keyboard moment.
Exactly. Well, you've hit on this dream humans have always had, but it's always run up against this massive engineering problem, hasn't it? How do you build something that's perfectly clear, lets you see out, but is also strong enough to handle the insane pressure down there?
It's a huge challenge. I mean, a really formidable one. The deep ocean is, well, it's brutal. And the materials we've typically used, they all have pretty serious drawbacks when you try to balance strength, clarity, and just surviving down there long term.
Which is exactly why this deep dive is zeroing in on something that sounds totally sci-fi, but, well, it's getting very real very fast.
Yeah.
We're talking about the potential of transparent aluminum for future underwater homes, labs, you name it. We're going to unpack the science, like what is this stuff? Why is it so critical for going undersea? And what kind of future does it unlock? Our sources today are pulling from some really recent breakthroughs, research hot off the presses, showing just how close this sci-fi idea might be. Okay, let's get into this. Stuff sounds amazing. So transparent aluminum. Like we said, Star Trek pops into mind immediately. But in the real world, what are we actually talking about here? It's not just one thing, is it?
No, that's a really important point to get straight first. Transparent aluminum isn't, a single material like you'd find on the periodic table. It's not literal clear metal. It's more of a category name, kind of an umbrella term for these super tough, optically clear ceramics and oxides. And they're all derived, one way or another, from aluminum compounds. These are highly engineered materials. Think of them as a big step up from your standard glass or plastics, especially when you need serious strength and perfect visibility. It's less about aluminum itself and more about how we process its compounds into something completely new, something much stronger and clearer.
Gotcha. So within that category, there are a couple of key players, right? Materials that are really making waves. Let's start with ALON, aluminum oxynitride. That one's been around a bit longer. Yeah, it's already out there doing stuff.
That's right. ALON is, well, it's kind of the established veteran in this field. It's a crystalline ceramic. That means its atoms are locked into this really ordered repeating pattern. Think like a perfect crystal structure. And that structure is a big part of why it's so strong and clear. Now, making it, that's the tricky part. It involves a process called sintering. It's not just melting.
Sintering.
You take these incredibly fine powders, like almost dust of aluminum, oxygen, and nitrogen. You pack them together under huge pressure, and then you heat them up. Really hot, like over 2,000 degrees Celsius. But, and this is key, you heat them below their melting point. The heat and pressure make the particles fuse together, bond at the molecular level. You end up with this incredibly dense, non-porous block with a uniform crystal structure.
So it's like welding tiny particles together with heat and pressure.
That's a good way to think about it, yeah. Ceramic welding, almost. And that uniformity is what gives ALON its amazing properties. And like you said, it's not just in labs. It's already used in things like transparent armor, replacing much heavier bulletproof glass.
Right.
And also in high-tech sensor domes, say on aircraft or missiles, where you need perfect clarity, but also something that can survive extreme conditions. It's proven tech.
Proven and seriously tough, it sounds like. When you say the properties are mind-boggling, what are we talking practically?
We're talking extreme levels of performance. ALON is way harder than quartz, and quartz is pretty tough stuff. It's almost as hard and scratch-resistant as synthetic sapphire.
Sapphire, okay. Like watch faces.
Exactly. So imagine a material that can take crushing pressure that would just pulverize normal glass. It can even handle ballistic impacts like bullets.
Seriously?
Oh, yeah. A sheet of ALON, maybe half an inch thick, It can stop projectiles that would need several inches of traditional bulletproof glass. And it does that while being way lighter and optically clearer.
That difference in thickness and weight must be huge for design.
It's massive, especially anywhere weight or bulk is a major constraint, like aerospace or potentially deep-sea habitats. It just opens up possibilities you didn't have before.
Okay, so that's ALON. Established, tough, impressive. But then there's TAlOx, transparent aluminum oxide. This feels like the newer kid on the block, the potential game changers, especially because of how it's made. It's very recent, right?
Yes, exactly. TAlOx, or specifically the way it's now being made, is the really novel breakthrough. We're talking about a newly demonstrated type of transparent oxide coating, and the manufacturing process is what's got everyone really excited. The big news, like our sources point out, broke early 2025. Researchers out of Ateneo de Manila University announced this technique they call droplet anodization.
Droplet anodization.
And it's not just about the material itself, which is cool. It's about this potentially revolutionary way of creating it.
And how does that work? Because, like you said, making ALON sounds incredibly complex and energy hungry. This droplet thing sounds simpler. Is it?
Yeah.
Or is there a catch?
Well, simple in concept, maybe, but highly sophisticated in execution. The basic idea is using these tiny microscopic droplets of acid combined with a low-voltage electric current.
Okay.
You apply these precise droplets to the surface of regular opaque aluminum. The electrochemistry does its magic, and it transforms the very top layer of that metal into a perfectly transparent oxide layer.
It's like enhancing aluminum's natural protection.
Exactly. Aluminum naturally forms a thin oxide layer that stops it rusting, right? This process supercharges that, makes it much thicker, perfectly clear, and incredibly tough, but it does it in a very controlled way, layer by layer almost, ensuring that uniformity, which is key for transparency. And this is the revolutionary production aspect. Traditional methods for ceramics like ALON, they need those crazy high temperatures or powerful lasers or complex vacuum chambers, all super energy intensive, very expensive to build and run, hard to scale up.
Great. Big industrial process.
Yeah, droplet anodization, it works at room temperature, ambient pressure, it uses way, way less energy. That makes it inherently much more scalable. You could potentially ramp this up for mass production far more easily and cheaply than ALON.
And greener too, presumably.
Definitely greener. Less energy, potentially fewer harsh chemicals involved depending on the specific acid used. This just blows the doors open on how and where you could use transparent aluminum. It could move from being this niche, super expensive thing to something applicable on a much larger scale, like for huge habitat windows or protective coatings on massive structures.
So the precision is still key, making sure those droplets are applied perfectly to avoid flaws.
Absolutely. The control over the drop plant size, placement, the current, that's where the finesse is. But the process itself is just fundamentally less extreme and more controllable than trying to sinter giant ceramic panels at 2,000 degrees.
Okay, this is where it gets really interesting for me. This TAlOx isn't just a cool new coating. The way you make it is a breakthrough. So if we put ALON and TAlOx side by side, what does this combination mean for actually building stuff underwater?
It's a fascinating contrast, isn't it? You've got ALON-proven, strong, load-bearing structural material. Great for windows that need to take immense pressure. And then you have TAlOx, this new, eco-friendly, super scalable coating with huge potential, maybe even for structural use down the line. This pairing really makes you ask, how can these two materials with their different strengths tackle the unique, just brutal challenges of the deep sea? Because like you said, it's not just about having a nice view, it's about survival, functionality, enabling things we couldn't do before in one of the most extreme places on Earth.
And yeah, let's talk about extreme, the deep sea. It really is something else. Building anything down there that lasts, let alone lets people live comfortably, it's got to be one of the toughest engineering gigs out there. So what are those main, fundamental challenges?
Oh, there are several big ones, all hammering away at any structure you put down there. First and foremost is the high external pressure, just the sheer weight of all that water overhead.
Right, the crushing force.
Exactly. It's immense. It builds up incredibly fast as you go deeper, just a few hundred meters down, and the pressure is already hundreds of times what it is at the surface. It's this constant, relentless squeeze.
Like being squeezed from all sides.
Precisely. Any material you use for windows, or even the hull itself, needs incredible compressive strength. It has to resist that force without buckling, cracking, or just imploding. It's a nonstop stress test.
Okay, pressure, check. What else is the ocean throwing at us?
Then you've got the corrosive saltwater environment. Seawater isn't just water, it's salty, full of minerals, dissolved gases. It's basically designed to eat away at stuff, especially metals.
Rusty.
Worse than rust sometimes. It causes electrochemical reactions that degrade materials, even specialized marine alloys, over time. It leads to pitting, weakening. This constant chemical attack breaks down protective coatings, gets into the structure.
Which means constant upkeep.
Exactly. Huge maintenance costs. You need specialized subs or divers just to go down and fix corrosion damage. It drastically shortens the lifespan of anything you put down there. It's like a slow, silent demolition job.
And beyond just surviving the pressure and the corrosion, there's a whole point of being there, seeing out, the need for light access. Why is transparency so vital beyond just, enjoying the fish?
Well, enjoying the fish is part of it. But seriously, optical transparency is critical for many reasons. Basic visibility for research is huge. Scientists need to see marine life, geology, what's happening outside clearly and without distortion. Direct observation is still vital.
Makes sense.
Then there's the human element, psychological well-being. If you're living down there for weeks or months staring at solid walls, it's claustrophobic, isolating. Natural light, a view of the outside world, even that watery world, makes a huge difference to morale and mental health.
Right, avoiding that tin can feeling.
Exactly. And then there are functional needs. Light is essential for things like photosynthesis, if you plan to grow plants inside the habitat, maybe for food, or air recycling using aquaponics.
Oh, like a self-sustaining system.
Potentially, yes. And finally, accurate sensor readings. Many scientific instruments need a clear line of sight, maybe through a transparent dome or directly through the main viewports. Whether it's cameras, environmental sensors, navigation tools, you need clear, distortion-free optics for them to work properly.
So pressure, corrosion, the need for clear views. The ocean is basically testing materials to their absolute limit. And the stuff we use now, acrylics, polycarbonates, even super thick glass, so they have real drawbacks, right? Why aren't they good enough for this grand vision?
They definitely have significant limitations, yeah. Let's take acrylic and polycarbonate. They're plastics. They're somewhat clear, relatively easy to shape, which is good. But they're soft.
Meaning they scratch easily?
Very easily. Not just from people inside, but from the ocean outside. Sand particles suspended in the water, bits of debris drifting by, even marine organisms trying to attach themselves or grazing on the surface. It all adds up. Over time, those viewports just get hazy, scratched up, visibility degrades badly. Trying to do serious science through a perpetually smudged window, not great. They just don't keep their clarity long enough in that environment.
Okay, so plastics are out for long-term clarity.
Yeah.
What about just using really, really thick glass, like those huge aquarium tanks?
That's a common thought, but aquarium tanks are usually at surface pressure or very shallow. For the deep sea, the kind of depths we're talking about for habitats, glass has to become insanely thick and heavy to withstand that pressure.
Right, the weight becomes a problem.
A massive problem. For a large window, a panoramic view, the sheer weight and bulk of the glass needed would be structurally prohibitive. The habitat design would be dominated by just supporting the windows. Plus, think about transporting and installing these enormous heavy glass panels deep underwater. Hugely complex and expensive.
And glass is brittle too, right?
Very brittle. While it's hard, it doesn't handle impacts well, and under that kind of constant, immense pressure, the risk of a sudden catastrophic failure is a major concern. So yeah, conventional materials, they just force too many compromises. They're not strong enough without being way too bulky. They degrade, they scratch, they limit the view.
So yeah, the ocean is a material's worst nightmare, and our current toolkit has some serious gaps. This is where transparent aluminum comes in. What does it offer that these traditional materials just can't?
If you step back and look at the big picture, what you need for a real sustainable underwater habitat is complex. It's not just strength. It's strength, yes, but also long-term durability, lasting clarity, reasonable weight for deployment, maybe even integrating other functions.
The whole package deal.
Yep. Exactly. And this is where transparent aluminum, both ALON and potentially TAlOx, isn't just a small improvement. It feels more like a potential paradigm shift. It brings together properties that were previously really hard, if not impossible, to get in one material. It offers this unprecedented balance that could finally unlock serious deep-sea habitation and exploration.
Okay, a paradigm shift. I like the sound of that. Let's dig into how it enables this shift. Starting with the big one, pressure resistance and structural integrity. How do ALON and TAlOx handle that crushing deep-sea squeeze?
Well, their inherent strength is the foundation. With ALON, its incredible compressive strength, remember, harder than quartz, tough like sapphire, means you can design viewports that are significantly thinner than glass or acrylic would need to be for the same depth rating.
Thinner means lighter.
Thinner means lighter, yes, which is a huge plus for the overall structure and deployment, less load on the habitat frame. But for the people inside, or the science being done, it also means a much better, wider field of view. Thinner material means less optical distortion, more light gets through.
So clearer, wider views. And it's safer because the material itself is stronger without adding all that bulk and weight.
Exactly. Better form, better function, better safety margin. It's a win-win-win on the structural front.
And TAlOx, we know it's a coating now, but you mentioned its future potential. How might that evolve for handling pressure?
Right. So today's TAlOx films are super thin, measured in microns. They're great coatings, but they won't stop the ocean's pressure on their own. But the way it's made, that droplet anodization, offers a pathway. The vision is that with more R&D, you could engineer thicker, multi-layer TAlOx composites. Imagine layering it, maybe laminating it with other strong, transparent materials, or even creating thicker, pure TAlOx structures if the process can be scaled that way.
Building it up layer by layer.
Potentially, yeah, or integrating it into a composite structure. If researchers can crack how to make it thicker or effectively bond multiple layers, TAlOx could potentially resist serious oceanic pressure, maybe rivaling ALON eventually.
Which would mean
It could mean enabling those really large panoramic windows, maybe even full domes, that we dream about for habitats, making people feel truly immersed in the ocean environment, not just peering out through a small, thick porthole. It's about changing the entire feeling of living underwater.
a totally different experience. Okay, so strength is covered. What about clarity and keeping that clarity? You mentioned scratching is a big issue for plastics. How does transparent aluminum stack up long term?
This is another huge advantage. Both ALON and TAlOx are incredibly hard and scratch resistant, way more so than acrylic or polycarbonate, and even more than standard glass.
So less worry about sand, debris, critters messing up the view.
Much less worry. That constant abrasion that makes plastic viewports hazy over time, it's significantly reduced with these materials. They maintain their optical clarity for much, much longer.
Which is critical for.
Critical for long-term research missions where you need consistent, reliable visual data. Critical for habitats intended for long-duration stays where you don't want the view degrading. And just critical for safety and operations, always having a clear view out. You avoid that gradual fogging up that plagues current systems.
No more looking through a scratched-up haze. Marine biologists must be dreaming of this. And optically, is it just about being clear to our eyes? Or are there other benefits, like for instruments?
Oh, definitely more. These materials tend to have excellent optical clarity, not just in the visible spectrum, what we see, but also well into the near-infrared NIR wavelengths.
And why is NIR important down there?
Several reasons. A lot of scientific sensors operate in the NIR range. Think thermal imaging, certain types of cameras for observing animals in low light, maybe even some communication systems using light. Having windows transparent to NIR means those sensors can work right through the main viewports without needing special separate windows or external pods, which can be vulnerable.
Simplifies the design.
Big time. Also, for things like internal aquaponics, ensuring the right wavelengths of light get through for optimal plant growth is key. High clarity across a broad spectrum helps with that. It just means better data, better internal systems, better visuals all around.
Fantastic. Okay, let's tackle the other underwater menace, corrosion, that relentless saltwater attack. How does transparent aluminum, especially TAlOx, help fight that battle?
This is a really neat benefit, especially with TAlOx. As we mentioned, aluminum naturally protects itself with a thin oxide layer. What the droplet anodization process does is create a much thicker, much denser, perfectly transparent, and incredibly robust version of that protective oxide layer.
So it's like super armor against corrosion.
Exactly. It's a transparent ceramic shield bonded directly to the aluminum surface. It physically prevents the corrosive saltwater from reaching the metal underneath.
Payoff is.
Huge reduction in maintenance, less need for costly inspections and repairs related to corrosion, much longer lifespan for the entire structure. It essentially acts as this permanent, clear, super durable sealant. You're not just getting a window, you're potentially coating the entire structure in a protective, transparent skin.
A window and a protective shield, all in one.
True.
Very clever. And we keep coming back to the TAlOx manufacturing process, that low-energy scalable method. How does that impact the feasibility of actually building these underwater structures?
It's Potentially transformative for feasibility. Making ALON is expensive, energy intensive, requires specialized factories. That limits its use, especially for really large structures where cost becomes a major driver.
Right, it's niche now.
TAlOx, with this droplet anodization, promises a path to much lower manufacturing costs. Because it's low energy, works at room temperature, it opens the door to possibilities like on-site or modular production.
You mean making the transparent parts right where you're building the habitat?
Potentially, yeah. Imagine shipping standard aluminum panels to the construction site, maybe a surface vessel or a coastal facility, and then using a portable or modular system to apply the TAlOx coating, converting those panels into transparent protected elements right there.
That would cut down logistics massively.
Hugely. Reduce transport costs, faster assembly. It makes the whole idea of building large-scale underwater installations much more practical, more economically viable. It could really lower the barrier to entry for deep-sea projects.
Wow, that is a game changer. Almost like 3D printing transparency onto structures. Okay, thinking about inside the habitat now. Energy efficiency, managing light and heat. Do these materials help there too?
They do, and in quite sophisticated ways. Because they're engineered materials, you can actually tune their properties. You can design them, for instance, to transmit visible light very efficiently, which you want for seeing out and for plants, but to block certain other wavelengths, like infrared or harmful UV radiation.
Why block infrared?
Infrared is heat. By blocking it, you reduce solar heat gain inside the habitat. Less heat buildup means less energy needed for cooling systems to maintain a comfortable temperature. That's a big deal for energy efficiency in a closed environment.
Ah, passive temperature control.
Exactly. And blocking UV protects both the inhabitants and sensitive internal equipment or materials. So you get the light you want, but filter out the heat and the damaging rays you don't. It's about optimizing that internal environment for comfort, for plant growth if you have it, and for overall energy balance.
So they're not just passive windows, they're like smart filters. Which leads perfectly into the really futuristic stuff. Smart windows and sensor integration. This is where it gets very sci-fi. What kind of integrated functions are we imagining here?
This is where the lines blur between a structural component and an active technology. Because these materials are stable and transparent, you can potentially embed other technologies right into them.
Like what?
Like transparent electronics. Imagine circuits, sensors, maybe even displays integrated seamlessly within the window itself. The entire viewport becomes an interactive surface.
Okay, my mind is slightly blown.
Right. You could have self-tinting viewports that automatically adjust their darkness, maybe to reduce glare or even to protect marine life outside from sudden bursts of light from inside the habitat.
Adaptive camouflage almost.
Or just light management. Then think about integrated sensors, turning every window into a real-time environmental monitor, temperature, pressure, water chemistry, maybe even bioacoustic sensors listening to marine life, all gathered right at the interface.
So the window is the sensor array. Wow, what else?
How about HUD-style augmented reality displays? Projecting data directly onto the window depth, navigation info, species identification popping up as fish swim by without blocking the view, merging the digital and real world seamlessly.
Like in a fighter jet cockpit, but underwater.
Pretty much. You could have embedded lighting within the panels for interior or exterior illumination, maybe layers for high-speed data transmission using light, and perhaps the ultimate integration, energy harvesting. Embedding transparent photovoltaic cells or thermal energy converters right into the windows to generate power from sunlight penetrating the water or temperature differences.
The windows become power sources.
Potentially, yes. Turning the habitat skin into an active energy collector, it's about making every component multifunctional.
Okay, let's pull this together. What does this all mean? You mean stronger, clearer, longer lasting, more energy efficient, and even smart windows and structures under the sea. It's not just about looking out anymore. It's about building a whole new way to live and work underwater.
That sums it up beautifully. And it leads to this crucial point. By solving these fundamental engineering problems with transparent aluminum, leveraging ALON's strength and TAlOx's potential, we're not just making better submarines or habitats based on old designs, we're fundamentally changing the equation. We're altering what's even possible for a sustained human presence beneath the waves. It shifts us from just visiting or surviving towards actually thriving down there.
Thriving underwater. That's a powerful vision. Let's paint that picture. What does this future look like? These habitats built with transparent aluminum. What's the experience? How does it change how we interact with the ocean?
Imagine stepping away from tiny, thick portholes. Instead, picture these expansive underwater research labs, or maybe even luxury eco-resorts with sweeping wraparound windows made from this stuff, domes even.
Floor-to-ceiling views of the reef.
Exactly. Visitors or scientists gazing out at vibrant coral ecosystems, maybe watching the strange life around deep-sea hydrothermal vents, all through panels stronger than bulletproof glass but optically perfect. The barrier between inside and outside just visually melts away. The ocean becomes your living room wallpaper, but it's real and dynamic.
It sounds incredible, almost like those concept drawings you see, but actually achievable.
That's the potential, yeah. Think about maybe an underwater city, okay, maybe starting smaller, a village with interconnected modules featuring these huge panoramic dome windows, crystal clear, strong as steel, maybe even self-cleaning. Imagine kids inside, pressing their hands right up against the transparent walls, watching sharks or whales glide by just feet away, feeling totally immersed and connected to that environment. Or scientists in a deep-sea lab monitoring experiments or observing behavior. Because of the view, it wouldn't feel like a cramped submersible. It would feel open, airy, connected. That psychological difference. It's huge for long-term missions.
Absolutely. And thinking bigger picture, beyond just places for people to live or visit, what other kinds of applications could this unlock? How else could it help us engage with this blue frontier?
Oh, the possibilities spread out quite a bit.
Yeah.
You could have highly advanced, fully transparent aquaculture farms. Imagine raising fish sustainably in contained environments where you can monitor everything visually, optimizing conditions, maybe even reducing reliance on wild-caught fish.
Better food security.
Potentially. Then, new generations of marine research stations. Permanent installations with unparalleled observational capabilities, allowing long-term, non-invasive studies of ecosystems we barely understand right now. You could even think about disaster-proof coastal shelters using the strong, transparent material. Or entirely new forms of offshore tourism. Imagine underwater walkways, observation pods, hotels offering views and experiences that are just impossible today. It really opens up the 70% of our planet that's underwater to more sustainable exploration, research, and maybe even resource utilization.
It's definitely clear this material could literally reshape our relationship with the ocean, turning sci-fi dreams into reality. But, okay, let's ground ourselves a bit. There's still hurdles, right? It's not like we're building Atlantis next week. What's the path forward, and what are the main challenges still?
Right, absolutely. We need to be realistic about the current state and the work ahead. With TAlOx, the big thing is, like we said, the current films made with droplet anodization are micron thin. They're amazing coatings, super clear, super tough for their thickness, but they're not yet load-bearing structures by themselves.
So you can't just make a big TAlOx window and stick it in a submarine hull yet.
Not yet, no. It's a fantastic protective layer, but it doesn't have the bulk structural strength needed to resist deep-sea pressure on its own, at least not based on the current demonstrated technology. That's a critical distinction. For structural parts, ALON is still the go-to, or we need further development with TAlOx.
Okay, so step one is figuring out how to make TAlOx thicker or integrate it differently. What does that involve?
It involves some serious materials, science, and engineering. Developing advanced layering or lamination techniques, maybe stacking multiple TAlOx layers or bonding them to a strong polymer core, or embedding TAlOx particles within another transparent matrix. Creating a composite that has the TAlOx surface properties but also bulk strength.
A transparent sandwich, basically.
Kind of, yeah. And then there's the challenge of manufacturing at scale, especially for large, curved shapes like domes. Doing that precisely without defects over large areas, that requires developing entirely new fabrication methods beyond just lab-scale demonstrations.
And the eternal question, cost. TAlOx production sounds cheaper in principle, but are these materials going to be affordable enough for widespread use, or will they stay in high-end niches?
Cost is definitely a factor. ALON is still quite expensive because its manufacturing is so complex and energy intensive. That limits it mostly to defense and specialized industries where performance trumps cost. TAlOx holds the promise of being much cheaper long-term because the process is inherently less energy-hungry and more scalable. But right now, it's still new technology. Ramping up production, optimizing the process, that takes investment. The expectation is the cost will come down significantly as it matures, making it viable for those larger projects, but it's not there overnight.
Makes sense. And beyond just making the panels, what about sticking them into a structure? Getting a perfect seal that lasts for decades under crushing pressure sounds tricky.
That's another huge challenge. Integration and bonding. How do you perfectly join these advanced ceramic materials to a metal habitat frame or to other polymer components? You need seals that are absolutely watertight, can withstand the pressure, the temperature swings, the corrosive environment for decades without failing.
No room for error there.
None. Any tiny leak or weak point could be catastrophic. So developing reliable bonding techniques and long-lasting sealants is crucial. And related to that is the need for extensive long-term durability testing.
Putting it through its paces in the real world.
Exactly. Lab tests are one thing, but you need to deploy these materials in the actual harsh marine environment for years, monitor their performance, see how they hold up to biofouling, abrasion, pressure cycling, all of it. You need that real-world data to build confidence for critical applications like human habitats. It's a long validation process.
Okay, so real challenges remain scaling up TAlOx, cost, integration, long-term testing. But despite all that, the overall feeling seems really optimistic, doesn't it?
It really does. The hurdles are significant, but the potential payoff is enormous. And the TAlOx breakthrough, specifically its low-energy, scalable nature, feels like it could genuinely unlock doors that were firmly shut before because of cost or manufacturing complexity. And having both ALON and TAlOx is powerful. You have ALON for proven, high-strength structural needs right now, and you have TAlOx as this incredibly promising coating with a pathway towards potentially lower-cost structural use in the future. It feels like a really comprehensive toolkit is emerging for tackling the deep ocean.
So this deep dive has really shown us how transparent aluminum, both the tough veteran ALON and this exciting newcomer TAlOx, is poised to completely change how we think about building and living underwater. We've seen its strength, its amazing clarity, how it fights corrosion, and its mind-bending potential for smart features. It really feels like it could take that age-old dream and make it real.
Absolutely. And hopefully we've given you a clear path through the science, cutting through the hype to see the real potential and the real challenges of this amazing materials revolution.
So, as you finish listening, maybe you're looking through a window right now, or at your phone screen. Just take a second and think about this. If TAlOx keeps progressing, if we can scale it up from thin films to strong structures, this stuff won't just be for habitat windows. Imagine underwater drones with perfectly clear, tough bodies. Imagine deep-sea power cables coated in it for ultimate protection. Imagine flexible, transparent electronics woven into underwater gear. It could usher in a whole new design philosophy for everything we put under the sea: integrated, durable, transparent.
Yeah, think beyond just habitats. Picture an entire underwater infrastructure, sensors, networks, energy systems built with or coated in this material, blending seamlessly, almost invisibly, into the environment.
What other hidden depths here on Earth, or maybe even beyond, could a technology like this finally allow us to explore and understand? That's something to ponder.